Hi, my name is Keith Makan, and my talk is titled Beyond String Theory, Symbolically Enhanced Reverse Engineering. So, let's get to it. The agenda, who am I? I'm going to talk about, why you should listen to me, what I've done. Um, I'm going to talk about binary reverse engineering, some of the hard problems that exist, why it's, challenging to actually just to walk through some binaries, what can make it really, really grueling process. We're going to talk about symbolic execution, and we can talk about what Angr is and how it can facilitate this, to walk through some of the basic steps in setting up a session. And then we can talk about some of the power that it has to help you find bugs, explore program paths autonomously, and actually automate some reverse engineering processes. And I got to talk about the hard problems before I get to Angr, so you're aware of that. And then we'll cover some applications that other folks came up with. Just quickly run through some of the cool things people have done, contemporary research. And at the end, if you want to ask questions, you can contact me. So who am I? I'm a security researcher. My name's Keith, as I mentioned. I do penetration testing. I do vulnerability assessment, source code review. It's my favorite. Reverse engineering is my favorite. So if you have code you need me to read for secure analysis, you want to know if there's any bugs that people can use to break it, or secure standards it's not adhering to, contact me. I've got a company set up to handle this kind of stuff. I also wrote 2 books. One of them is called the Android Security Cookbook, which I released in 2012. It has, it's a collection of recipes that you can use to break open an Android app, reverse engineer it, and assess it for vulnerabilities. And the other book I wrote is called The Penetration Testing with a Bash Shell, and it's basically also a collection of small recipes that make it easier to use Bash for automating penetration testing tasks. And currently I'm working on my master's, which focuses on symbolic execution for race condition detection. So I'm going to use a symbolic execution engine to autonomously find race conditions in binaries. Some quick terminology. Reverse engineering, I'm going to throw that word around a lot. It's basically the process of unpacking a program to detail its behavior. Here we're focused on binary programs. Okay, and if you're unpacking a program's behavior, you're going to have a lot of this word thrown around, a block of a program. A block is just a contiguous section of instructions separated by jumps and calls, conditional separations of stuff. You want to know which blocks follow which. And if you're going to do that, you want to know the precedence of blocks. You're going to have to derive a control flow graph. And this is a directed graph that shows you which block will follow which and how they'll branch and split off into one another. Very important if you're doing reverse engineering. And again, we're going to talk about symbolic execution. And symbolic execution is all about the association of symbolic states. And a state is basically a hazy collection of instructions which loosely represents a block. It's associated to a set of metadata, which is vector register memory values. So you can make sense of what will happen when you reach the state in the program. A block doesn't have that, so this is why I'm saying a state is this association of metadata. So the typical process with reverse engineering, you typically load up your binary if it's loadable. You might have alf sections or things that are broken. Program load statements that are all messed up in the wrong place. But you load it up in binary, the binary in Binary Ninja, either Pro, Hopper, Hydra, Redari, what have you. There's a suite of tools now that make this very easy. You would then typically check the strings, try to disassemble stuff, do cross-referencing of function calls and variable references. You try, hope that there isn't a lot of obfuscation that makes this hard. In terms of like complex CFGs, obfuscated function names, etc. And you hope. That's kind of the general approach. But so this is the typical process. But what makes this hard? Number one thing that makes it difficult is complex CFGs. So if you're trying to, in your head, derive what will happen in a CFG, these are the kind of hard edges to the problem. You could have nested loops. And if you don't know what this is, like I just took a snapshot of a binary I was looking at, and these blue lines, they're all individual ways to enter a loop. So if you're reading this by hand, you can understand this is going to be extremely grueling, making sense of how this loop actually behaves in summation. The other thing that makes it very difficult is complex pointer arithmetic. So you might have these references to memory based on registers that are, summing and multiplying and scaling, indexing and basing, based on registers that take a long time to work out where exactly in memory this is trying to point. And here we even have like a complex pointer arithmetic for a comparison to break up a block. You might also have data-dependent branching and calling, and here is an example from a CTF, but it's not so uncommon to happen in actual real-world binaries. What this does is fgets it calls fgets, which reads a string from a file descriptor. The file descriptor we're using is stdin, and it's actually writing this into the stack, the result, and then branching to that part of the stack as though it's a valid function pointer, which is pretty harrowing and like a glaring example of a code execution vulnerability. But it means that if you're actually reverse engineering this binary, you're not going to know what will happen, just by reading the source code in a straightforward way. So why are we looking at binaries? Why are binaries so important? Well, there's a big schism between source code and actual binary behavior sometimes, and you can see this in terms of how security people have panicked about compiler optimizations over the years. And one of the good examples is something called memsad, which is vulnerability or a kind of a lack of code etiquette that causes optimizations to remove certain secure operations. So in this example, we have a password that's being stored on the stack in the PASSWD variable. And at the end, you obviously don't want to have this lying around in the stack, so you try to clear the variable. You want to mem set it to 0. But unfortunately, under certain compiler optimizations, it will actually just remove this mem set, because the compiler checks that you're referencing a variable you're not going to use, so this operation is useless to me. I don't need to actually run this mem set. It's setting it to 0, and you're not using it. It'll optimize it out, which means that password will stay on the stack. And if you still don't know why this is a problem, you've got to think about problems like stack leaks, things like heartbleed, things like out of bounds reads. Those kind of things make this very, very dangerous to have lying around, especially for sensitive data like a password. Another glaring example, which I stole from someone's blog, is this idea that when you have two threads working on something at the same time, a typical setup is that you have a context variable. So CTX is the context, and it has a variable n, and in this nested loop, n is going to be used to exit that loop. So when you have this data and you mod it by 2, you check if it's even or odd. Another thread will actually flip n on and off. So it'll make it 1 or 0, and you can control essentially when this while loop will exit. Otherwise, it'll just keep spinning in that while loop. Now, when you compile this into a binary, it turns out that compiler optimizations can drastically change the picture of what's going to happen in that indefinite loop. Because look at the code again, you're referencing this n, and in the compiler will have different optimizations for it, because in this function, n doesn't change. You don't actually change n, something out of context changes it. So what happens is when you compile this under certain optimizations, it drastically changes the picture and will actually introduce an undefined state that can cause a memory a race condition, because it just skips the check of the sentinel entirely and just makes like an indefinite loop. So this will introduce a race condition if you're not entirely sure. So on the one hand, you're checking it faithfully. On the other hand, you optimize so aggressively that it says, oh, you're not going to change this n variable, so it optimizes out completely. So that shows you there's a chasm that can open between binary and source code, and you probably want to check your analysis against an actual literal binary definition before trusting that the source code is secure or not. So just a summary of the hard problems in reverse engineering. You have binary formats that need to be interpreted, and the other kind of key point is derivation of control flow graphs are very hard, because you have data-dependent branching, complex pointer arithmetic, dynamic loading and resolution, and optimizations that can change the view. So now we know it's hard about reverse engineering, but symbolic execution, this kind of new emerging technology, not really new, but like for analyzing binaries, it's pretty contemporary. We can now approach these problems in sort of a scientific way, chipping out different program exploration methods, chipping out carving out the slow approaches of symbolizing program paths and analyzing things like algebra and constraint solving. But so what is symbolic execution? Before we can get to how this is going to help reverse engineering, symbolic execution is basically a marriage of two pieces of technology: constraint solving, which exists in formal proof theory, formal logic. It's a way of automating theorem proving for certain fields of mathematics, and it's a way of verifying circuit behavior for people who engineer hardware. So if you actually bake your own chips, you write your own Verilog, there's all these tools that exist for checking that your Verilog circuit is not going to have certain states, and the way it guarantees it's not going to take certain states under given input is by relying on constraint solving and symbolic execution as well. And it marries this old constraint solving technology with the big scary new source code analysis we want to do these days, and it kind of sandwiches them together. But essentially the process is it takes the variables, the if statements, the conditionals, and the various states a program can have, and it distills that into stuff that a theorem prover, constraint solver will enjoy working through. And if you don't know what constraint solving is, just a quick crash course. It's just a reference to the Boolean satisfiability problem in computer science, which is basically the problem of given a formula of Boolean variables, ands or ors and XORs and all these kind of Boolean operations. Can you work out the vector of bits that will evaluate that to true? And when you talk about SMT solving, the terminology becomes: can you determine a satisfiable solution to this, or determine that it's unsatisfiable? There's also a third option, because this doesn't have a definite approach. There's no approach to this problem that will for any formula be able to say, yes, you can definitely solve it, no, you can't. There's certain forms that will break down and become solvable, and certain forms that won't. And the third option will be, it's I don't know. I don't know if it's satisfiable, unsatisfiable. There's a third answer that can come out, and this basically happens when the SMT solver gives up. It says, I got it. I don't know how long I have to guess, but it's definitely too long, and it stops guessing it. This is directly related to the halting problem. You can reduce one to the other, or dress one up as the other problem, because if you can answer the Boolean satisfiability problem as we see here, you're saying that, like, why not just reduce a program and its variables to this form, thereby solving the halting problem. If you're looking for halting in a program, you can contrive it as a Boolean satisfiability problem, or Boolean satisfiability problem can be dressed up as a halting problem, or what have you. And the basic process of constraint solving is you take all the conditional statements again, as we see in this picture here. You start with a C program, you rewrite those variables and the if statements in a way that's friendly to conversion to constraints, which is here the person is doing single static assignment a form, which means like each variable is only assigned once. You don't have like multiple assignments for the same variable. And once that's there, you can more easily convert it to Boolean constraints. You're going to break this down into symbolic bit vectors. When you have an int, you're not going to just have one variable. You're going to have a variable for each bit in the int, and break it down like that. Not going to get into the mechanics of it too much, but you're converting a program and its conditional statements. Because let's say you have if statement, nested if statements that reach a certain place. What will happen is, if you want to know what's required to reach that place, you'll actually have to latch on to the variables, these conditions of if this and that if statement and this if statement and this. This is why you see these upside down kind of lambda looking a kind of symbols. That's the and symbol. I don't know if my mouse is going to record now, but this is the and symbol, and this is how you can see various if statements get latched on in a program path. We'll talk about a program path in a second. So the basic process is that you're going to take a C program or a program. In our case, it's a binary. It doesn't matter what the source type is. This works for any programming language. It works for IR, intermediate languages. And as we saw, it works for hardware language. If it works for Verilog, then surely it'll work for the the higher level languages as well. So you basically have, if you want to describe a symbolic state and build a symbolic state map, you're going to have three things you need to describe. One is the variable store, two, the path condition, and you're going to have to be able to describe the state as unique. You're going to have the state ID. You don't want to confuse states with one another, so you'll have to be able to uniquely identify them. And the way this works is, as you encounter statements, you symbolize the variables involved, and you record the path statements required to reach those statements. So our first state is representing the path that's required, the stuff that will, it represents the way that the variable store will be affected, and the path condition that needs to be satisfied to reach statement 1, 2, 3. That statement, program statement 1, 2, 3. That's symbolic state number number 1. And you can see in the variable store, all we've done is symbolize x and y. We said x has to be symbolized as a, and y has to be symbolized as b. And the path condition is just simply a true, because nothing needs to happen to actually reach it. You'll always reach it no matter what. So it's just a true. And then at the bottom, just for documentation's sake, we're showing the program state associated to this. Now, when you encounter an if statement, this is very important, you can actually envelop both sides of the if statement in analysis. You can immediately have a view of both sides of this if statement when you want to make decisions. So imagine fuzzing using this. Like, you're not going to have the fuzzer blindly guess, like, oh, just guess until you get both sides. The fuzzer can actually have view of, if I want to reach the one side, I'm gonna look at state number 2, the successor state, and I'm going to say, okay, my path variable requires symbolized variable A plus symbolized variable B to be bigger than 10, and it's going to mean that my variable store will update in this way. Once I've reached it, it'll update A as B minus 1. And so the other side is just a not condition of that. It just says A plus B has to be smaller or equal to 10. Okay, that's the not condition of the other side. So now we immediately in view have both sides, and we can decide whether they're interesting. Like you can say, is it interesting to our analysis that A should be B minus 10? We don't want to subtract too much from Y. Maybe in our path, we know that for our analysis, we want to look at all the cases where Y is only subtracted from once. So therefore, the only paths we're going to be interested in is the ones where Y it doesn't have the subtraction. You can immediately see that here from just looking at the if statement. So that's kind of the power of this analysis. But this is how we build the path conditions. We update the variable store, and we associate the program statements to it so we can make decisions going forward. So you need to imagine this map, but like involving thousands of different states. And again, states will grow pretty fast. They can grow so fast, in fact, that they overwhelm a analysis, and that's called state explosion. Because as you've just noticed, every time you introduce another state, another if statement, you're gonna fork that state into at least two successors. You could have if then else, or if then if else else. Else if. You could have a bunch of different if statements, which means you explode into even more states. And what they can do is actually make sure that your analysis has so many paths to look at that it just becomes infeasible to look at all of these paths, and that's called state explosion. And obviously the other problem with this is that it's dependent on constraint solving, which means you have to churn through an undefinable amount of time to actually get your answer. So there's just two hard edges to it, which we have to rely on optimization problems to get around. And they're pretty elaborate optimization problems. You can cache constraint solving results. It turns out that normal programs, they don't tend to have wild, introduction of variables. In if statements, they tend to incrementally add conditions. So you would say if A is bigger than C, and then the next time you're not going to do X and Y, maybe you're going to be if A is bigger than C or bigger than D. You'll kind of latch on to a core form. Core form of constraints. You tend to pick up little adages of constraints, which means you can probably reuse solutions every time you ask a question. It's very useful. It turns out to do that. Then there's also something called state merging, which means that like if you split a state, if statement, and let's look at the previous example again. It's a good example to work from. If you split the successor states, you'll see that in this program they end up reaching the same point. They're both going to reach the same return statement, which means if you don't have any use, let's say there's a longer program beneath this before the return statement. If you don't have any use in maintaining both paths and latching on the same information to both paths, you can just merge them at the end and say, okay, these split at a certain point, but they merge again because both sides will exit the same if statement, essentially. And that's called state merging. It avoids having to maintain two separate paths that will behave exactly the same. And then there's also directed exploration methods, randomized exploration methods, which tell you, like, look, you don't have to explore every single path, go down every single state association or follow every single direction in the state map. You can just stick to the ones that are interesting to your analysis. For instance, you can explore states that will always end in a mem copy, and there's ways to optimize it so you never step down states that don't end up there. That's called directed execution, which I'll show an example of in a second. Now, I talked about state explosion, and this is what it looks like. This is a typical map of some random binaries on an Ubuntu 20.04 machine, and what happens here is I'm graphing execution steps, which is the x-axis, versus active state, which is the y, and I'm showing how fast they grow. So you can look at kind of in relative terms how many steps you'll get before you probably start exploding. So the yellow line, the first yellow line, obviously that's exploded. Like you're never going to get to 50 steps unless you maybe have a supercomputer, right? Like it grows pretty fast. And as I said, it's an exponential graph. It's a logarithmic graph. So it looks like a logarithmic graph. So this kind of tells my makes my point pretty succinctly. And so this is another picture of how states grow. This is something I put together with a little tool I wrote, again based on Angr. All it does is step through states. It collects up the symbolic states and works out how they're associated to each other in a directed graph format. So you're looking at one state becomes two states and is reachable from this state to that state. This is actually how this works. It's kind of like a CFG for symbolic states. On the one side we have GNU debugger, and you can see the actual point where states start exploding and growing at an exponential rate. On the other hand, we have object dump, and the interesting thing here is there's definitely loops that you can see just loosely with your eye in the GNU debugger picture, and that's obviously because GNU debugger actually wants to run a program that could happen indefinitely. So you'll definitely have loops that try to iterate the program over and over. And on the other side, you have object dump, which isn't going to run anything. It's just going to read a file, and if it doesn't see what it wants, it'll exit. So you're looking at this, this nice dragon on the one side and a scorpion or something on the other, or what have you. But it's interesting to see the actual behaviors reflected in the symbolic states. It's very, very cool. So what is Angr? Well, basically Angr is a collection of technologies. It comes from some technology that was submitted to the Cyber Grand Challenge that DARPA hosted in 2016, and basically it came together as a bunch of stuff that was meant to help automate vulnerability discovery in binary programs. And the technology that is involved is, first of all, the Capstone disassembly library. So when you throw a binary in, Capstone is going to be doing the heavy lifting in terms of disassembling and making sense of actual executable format. It also relies on something that the Angr team wrote. The Angr team's from UC Santa Barbara. The other thing that they contributed, in-house to this is CLI, the actual binary loader, which stands for CLI loads everything. If you have a Unix beard, you kind of know about these cool recursive acronyms. CLI is trying to evoke memory of those. And the IR language, if you know anything about compilers, you know that an IR language, or intermediate representation language, is going to be part of this whole process, and the one that this is based on is called VexIR. So it's VexIR comes from Valgrind, the Halgrind technologies. It's stuff that used to, I believe, Thread Sanitizer used to be based on this stuff, and then they moved to LLVM. If I'm not mistaken, but VexIR is integrated into a lot of different projects because it just works well, or used to be. And if you want synergy with those things, you want to implement the solutions that they implement for program analysis. You can immediately do that in Angr now because of the way that they supported this stuff. And to turn vexIR into something that a constraint solver likes, it relies on something called clarify, which takes types and spits them out into, like if you have an integer and you want the integer to be symbolized, it'll spit it out into Z3 in a way that it likes, so you can actually solve constraints based on that. And Angr is the thing that kind of mediates this whole process, models memory, associates stack, and block count, depth, and all these nice things to the actual constraint solving you're doing. And obviously, if you want to actually host a session in Angr and symbolically execute a binary, you're going to need to know about three key things. The first one is the project, the Angr project, the simulation manager, and the sim state. What happens is you load your binary up into a project, you set up a simulation manager, and you step through simulation. The simulation. I'll show you how that looks in a second. And out of that step will come Angr states, sim states. And the sim states allow you to evoke the solver. So once you have a sim state, you can say, hey, solver, from the sim state, what do I need in terms of my symbolic variables to reach this sim state? And you can also look at what the registers will look like, what the memory will look like in that state. You can even add your own plugins to this process as well. As I mentioned, I haven't mentioned this yet, but the simulation manager has stashes. So the stashes will have active, dead-ended, deprioritized states. There's a couple of categories. You can even add your own stashes arbitrarily if you want. It's just an associative dictionary, but the default ones that you need to know about are the active, dead-ended, unsatisfiable, and unsatisfiable states. Those are, I think, the ones you're going to be worried about the most. The active states are the ones that can still be stepped forward in execution. The dead-ended ones are the ones that aren't, and the unsatisfiable states are the ones whose constraints are not satisfiable. And there's also like unconstrained states, states that I believe rely on symbolized input. But you can also stuff into the simulation manager exploration techniques of your own, which there's some nice built-in exploration techniques already, things that help you save memory, that keep the program going. There's things that actually direct execution towards certain program states, and I'll show you how they look in a second. But that's basically the spiel. So the workflow is pretty simple. You're going to load a binary into Angr, and this is what the Python looks like for that. Very simple. Angr.project, give me a binary. And at this point, I'm not going to show this now, but you can derive a CFG. You can check out the sections and the symbols and expect actually the alpha properties of the binary, and ask questions around that. The second thing is, like, once you have your binary loaded, you want to build an initial state, and as you can see here, your initial state, you just go project.factory, give me an entry state, and you can actually ask for a full state where everything is symbolized, a blank state where basically nothing is, and a custom state, which is whatever you want to symbolize. Here's a custom state I'm kind of building where I'm saying, look, I want argv, I want to symbolize argv, the array, and I want 8 position. I want arg count amount of argv arguments, and they got to be 8 bits times whatever length I give it, and I'm also naming them arg something, arg1, arg2, arg3, whatever. And then you just stick that in the entry state, and Bob's your uncle. The other thing that I'm mentioning as optional here is you can actually hook symbols. So you can tell it, hey project, whenever you're in execution and you reach, let's say, pthread create, please call this function. And once you call that function, it's called a sim procedure. You can actually call another function if you like, do a bunch of stuff with the arguments, return from whatever call you made, then continue executing. It's basically like hosting a breakpoint in a debugging session, if you like. So you build the state, you model your variables. Kind of this is already shown in the previous slide, but modeling variables means modeling files, registers, memory, environments, and what have you. And once you have your binary loaded, your environment modeled, you can just step through the simulation manager. And this is straightforward how you do this. You go angr.simulationmanager.step, and you tell it, hey, the stash I want to step is this stash. It doesn't have to be the active stash. It can be the unconstrained states. It can be the unsatisfiable states. States. But for argument's sake, you probably, by default, you'll be stepping through the active states. And let's look at a quick example. Now, the typical thing that you do when you get a binary is you maybe want to check the static strings. That typically tends to get you some metadata on what to expect. It'll tell you like, oh, it's going to print this string somewhere and it's going to do something with that string somewhere else. So it gives you some semantic information, not much. There's not much context to it. But here's an example where that wins you nothing. If you look at this binary, it's checking argv against the string called kmsec, and anyone can tell you if they can read C that it basically wants argv1 to be the string kmsec. But if I strings this, I will not see the string kmsec. I'll not see that at all. But when I run this in a tool that I wrote based on Angr, it very easily works out, to get to that string copy. And again, this is the directed execution I was talking about. The tool that I wrote here called Spore Crawler will actually go through the binary and work out how to get to memory sensitive calls. So it'll look for, how do I get to mem copies? How do I get to mem sets, string copies, string n copies? How do I get to functions from a known execution state, which is like just the first executable state? How do I get from that to these dangerous functions? And what does my actual input need to be? So if you read code for vulnerabilities, this is extremely helpful because it means you don't have to go and cross-reference in the binary on your own. You could be cross-referencing stuff that will never be reached, and it'll take you ages to work that out because of those difficulties I mentioned earlier on. But here, Angr is automating that process completely. It's telling me immediately you reach the string copy by giving it this string in the argv variable. And another CTF example of this, that was a contrived one, but here's a simple CTF example. Just if you're using symbolic execution to solve a CTF, the process is incredibly simple. And I'll show you how this works. First step, you want to disassemble it just to get a picture of it. You don't have to, but you do want to kind of see where are we going to aim our session, and it means you need to at least be able to see where certain stuff happens in the binary. And a quick read of this one will show you, hey, it's going to end up in putting either a bad string it's going to print out either bad or good. We obviously want to get to good. So we might not even know this. We might not even know that which one is the good and bad, because if you look at the actual disassembly, here's the two puts instructions, and we don't know really which one's good. But what we can do, because of the power of symbolic execution, is we can just breakpoint at the string compare, and we can say, hey, the reason we want to breakpoint here is just so that everything that needs to be loaded and referenced is there for us. It's not always true because of lazy loading, but this typically means you got everything in front of you that you need once you breakpoint in context of the actual program run. So just to make things a bit easier, I'm going to breakpoint right there. There might be other debugging tricks you got to get around, but for our sake, we're just going to breakpoint there. And then we're going to say, look, I want to target one of these two puts calls. So I want to ask Angr, hey, how do I reach one of these two puts? So just for argument's sake, I'm going to guess that plus 143 in the listing at address 0x417. I'm going to guess that that's a good one. I'm going to tell my symbolic execution tool to search for whatever I need to get there. So this is what you're seeing with SciDB search. So it's this is a GNU debugger plugin that I wrote based on Angr, and it's going to target just that. It's going to go, hey, tell me what input I need, and it actually here you can see it work out that you need to put into stdin, not even one of the args. It worked out that you've got to put into stdin the string, and that's exactly what I do. And you can see here in the sort of chopped out screenshot on the left over here, you can see that it actually worked it out properly over here. Yeah, my mouse is there. So that's incredible. I just told it, go for this. Is this the right answer? And it was like, yes, you solved it. So just reviewing what we just did, it's even, sort of embarrassingly quick to describe what just happened, but that's how powerful it is. You kind of can automatically discover input paths. You can target, you can work out what's required to reach memory sensitive calls, thread calls. If If you have specific functions that are unique to your binary, you can hook based on those as well. And you can even, if you don't have program symbols available, you can actually filter through paths based on other metadata. You could say, look, my fuzzer seems to get stuck at this block depth, so I'll let the symbolic execution engine run until it reaches, that block depth plus 1. Or I'll let it run until the EIP is at least calling this library, etc., etc. You have all this metadata that you can rely on to automatically explore the binary. So let's make it pretty powerful. And this ability to ask whether states are reachable is extremely powerful because you can now do amazing things like automatically generate exploits, which I'll show you. I'll show you a reference to a paper in a second that does literally that. Like it uses Angr to, there's a tool called Angr ROP that actually takes your binary and works out ROP gadgets with certain properties for you automatically. So forget Mona.py, that was the old classic back in the day. Mona.py works out everyone's ROP gadgets through like glue and tape and very archaic methods. But this one actually uses symbolic execution to churn through a constraint folder to work out exactly what you need from your properties, from the properties of the ROP gadget. It's a much more autonomously suited process. And the other cool thing that's cool is with symbolic execution, once you know the path, you know the actual test case. And you can sometimes do this without running the program at all. You can take binaries that are for obscure environments that you don't actually have the metal to run, and you can learn very elaborate things about them, without the actual environments again. So another cool example of this whole spore crawler tool that I was talking about in the previous slide is just so you get the idea. It shows the associated sim state, and this you can use to work out the actual memory address that's being called, or the block that this thing applies in. It shows you the blocks. Here we have a lot of mem copies in the same block. It shows you the actual arguments as well. And there's a bit of a trick to making sure you actually interpret the arguments properly, because they come they might come from the solver as like an unconstrained state, or they might actually have to be worked out through again solver interaction. But you get all this context to where things are referenced. And here's another example of that. These mem copies are referencing strings, and because I run this tool, I immediately know what those strings are being used for. So if I see a file name here, it's not just an empty string in the binary that I have to kind of like hope will be called. I know immediately it's reachable. I know it's referenced in a mem copy, and then I know, well, I want the fuzzer to target this file, right? Like I want the fuzzer to open this file and do all kinds of crazy stuff to it, because I definitely will be hitting like lucrative code. So that's the kind of elaborate power it gives you. And just to close, I'm going to talk about some of the other applications. There's this really cool project called Firm USB, which someone used, I believe someone used Angr in this case, to search through USB firmware using symbolic execution. And basically what it does is it checks for cases of bad USB. So bad USB was when you have these USB devices that pretend to be multiple different peripherals. So what this program does is it looks at the firmware of the USB and says, hey, you've got all these different descriptors for USB functions. Do you actually use them in reachable code? And if you use contrasting descriptors in reachable executable code, again determined by symbolic execution, then we know you're a piece of malware. Like why would a sane USB tool have all these different descriptors? It doesn't make sense. Obviously, it's down to you what's a sane set of descriptors. The other thing that people have done that's pretty cool is Clee Spectre. This is not based on Angr, it's based on Clee, another symbolic execution engine. But basically they said, hey, symbolic execution can unearth all these different properties of reachable code. So we want to see if there's actually cache implications that make Spectre sort of exploitable for the code. Another cool example is just general cache side channels being available in code. And again, the novel example I like is arg, which actually uses symbolic execution to generate return-oriented exploit payloads. So it takes a binary, it strips out all the gadgets, and then it uses, it combines them under certain analysis, and then solves for which one should come before which one using symbolic execution if you want your program to behave a certain way. So that's very, very cool. So these are my references. Please go look at them if you want a lot more elaborate, discussion on symbolic execution and its applications. I also want to make sure that people know where I stole some of my cool pictures from. And yeah, that's it for me. That's my website, that's my blog, and my GitLab. Thanks for listening. I hope everyone had fun.